Hello everyone, I'm Yu Hao from University of California, Riverside, and I'm excited to share our paper, Syscall state-of-the-art operating system kernel father has found more than 4,600 bugs in the Linux kernel over past few years. One necessary component of Syscall is the collection of Syscall descriptions, which includes the Syscalls, the argument of them, and the dependency between them. However, to our knowledge, current Syscall descriptions are largely written manually, which is both time-consuming and error-prone. So we now show an example Syscall description for the KVM driver, which includes the following necessary components. The first one is the Syscall interface, which allows user space application to interact with the driver. For example, the Syscall open, IO control, also could be read, write, and others. The next is the device file name, which is used as an argument in Syscall open. For example, here is /dev/kvm. The next is the command value, which decides the sub-interface of the IO control, and is the value of second argument of IO control. Treating them as separate Syscall interface allows Syscaller to generate test cases more effectively. And the next one is the argument type, which are other arguments to the Syscall interface. The last one is the explicit dependency between those Syscalls, mainly involve the file descriptor being returned from one Syscall interface, for example, return value of Syscall open, and used in another one, for example, the first argument of the IO control. So explicit dependency allows Syscaller to generate valid test cases. Note that the file descriptor can also be returned by Syscall IO control for those complex device driver. We refer to such dependencies specifically as non-open file descriptor dependency. So since current Syscall descriptions are largely written manually, and not all kernel drivers have manually created a Syscall description, especially compared to the core Linux kernel. The kernel driver accounts for about 70% of the line of code of the kernel. So the goal of this work is to replace this step. So we designed a new tool, SyzDescribe, which is able to statically, accurately, and automatically generate a Syscall description for the Linux kernel driver. SyzDescribe only needs the compatible kernel or module, and it can directly generate a Syscaller compatible Syscall description. The generated Syscall descriptions are better than manual created Syscaller description in some degree, and closest to the ground truth. So the key insight of SyzDescribe is that we summarize and model the programming convention regarding the kernel driver development. This allows us to understand how a kernel driver is initialized and how its associated interfaces are constructed. So at a high level, we can then statically reconstruct the initialization of a kernel driver by faithfully following the summarized initialization process. The core design of the SyzDescribe is based on the modeling of the well-established contract between the kernel and the driver. So we have two analysis phases. The first one is the kernel module analysis phase, and the second one is the Syscall handler analysis phase. So in Linux kernel, drivers are in the kernel module. Each kernel module has a well-marked entry and exit point, usually defined by micro, such as the module init and the module exit. Also, there are some others. A single driver is usually defined within one single kernel module, and the SyzDescribe detects kernel module by their initialization functions. For example, here is the module init at line 16. So then SyzDescribe recognizes the existing of any kernel driver and recover the basic interfaces. There are three first-level types of the device in Linux kernel: character, block, and net. So in our work, we consider the character device and block device because they can be accessed from user space by the device file in the /dev. So as shown in the figure, there are two key types of the objects that define during the initialization of a kernel driver, which are driver object and the device object. And they collectively define the basic driver interface. Our goal is to identify those two types of objects and associate them. So To pair the two types of object, we rely on the device number assigned to each type of object. And the device number not only uniquely identifies a device and its file name, but is also associated with a set of Syscall handlers, for example, the IO control or open. So then we can simply inspect their related critical fields to recover what we need. Syscall handlers are stored in the file operation structures, which are assigned to the driver object in the line 22, and the device file name are stored in the device object in line 25. So then when there are Syscall open and the Syscall IO control from user space on the device file in the line 25, they would finally call the Syscall handler at line 18 and 19. So to summarize, we need to find the device object, whose type is the structured device, and the driver object, whose type is the structured CDL or Jen disk, and their device number. So we can then get the operation structure for Syscall handler and the device file name. Somehow in real Linux kernel code, the situation would be complex. It's possible that they look like different. For example, all those things are packed inside one big structure like the MISC device, which is a subcategory of the character device. But however, fundamentally, they are the same as the structure above, so we can still handle them. For each discovered Syscall handler, SyzDescribe attempt to recover the additional detail about those interfaces. This includes the command value, argument type, and the additional Syscall handler from the IO control. So in addition to the module unit function, Syscall handler themselves can also create additional Syscall handlers. This is most common in the Syscall IO control, where additional file objects are created. So inside a file object, there is a pointer to the structured file operation object, representing the corresponding set of Syscall handler associated with the file object. In addition, as shown in the figure above, a file object is paired with a file descriptor that will be returned to the user space. For example, in the figure below, from line to 37 to 41, we can say that there is a file descriptor and a file object, and they are paired through a specific function called file install. Finally, after all those things, SyzDescribe can directly generate Syscall description used by Syscaller. And to evaluate the SyzDescribe, we inspect the gap between the SyzDescribe and the ground truth. We randomly pick 100 kernel driver as a data set. We can say that SyzDescribe is the closest to the ground truth in all aspects. We then have a deeper comparison between the SyzDescribe and the manually created Syscaller description. Because 57 drivers are missed completely in the manually Syscaller description, so we choose to include a subset of drivers that are covered by the human, which is 43 drivers. Overall, SyzDescribe find more command value and argument type for 3 drivers. We then analyze those 13. We then analyze those 13 drivers to understand that those possible bugs in the human-generated description. SyzDescribe recovered 78 missed command value or argument type. We also found that there are 2 false negatives of additional Syscall handlers in the human Syscaller description. And for the false positive, mainly because of the evolution of the kernel code, because kernel code will be updated. Only one of those bugs is eventually fixed on the January 2022 before we started to report bug to them. And the result means that ongoing maintenance is needed. Besides, we also find that there are still false negatives after human updated the related Syscaller descriptions, which means those bugs have existing for a really long time. And so the human experts are not enough. So far, we have reported all the bugs to the Syscaller, and all of which are fixed. And we also share the Syscall description generated by SyzDescribe to them. And those are the finding results for the Linux kernel. And overall, we pick 30 out of the 100 kernel driver based on whether they are bootable in the QEMU. And for 10 out of the 30 driver, they do not have any Syscall description. And for other 20 drivers, SyzDescribe and the Syscall description are compatible. And the ground truths are always better, so the coverage may not overlap completely, which means we can still improve some human-generated Syscall description. Then we also directly apply the SyzDescribe to generate a Syscall description for the Android kernel of Pixel 6 without any human effort. All of them are automatically and find 18 crashes. And here are some examples of the bug found. So that's all of my presentation. Welcome. Any question and discussion?
Wow, very cool. Questions from the audience? Oh, there we go. Yeah, see?
Have you ever known the paper in NDSS this year? I think no grammar, no problem.
Yeah, I know that.
So I wonder, I know with grammar, the performance will be better, I think. How do you sometimes it seems we need very generic way to fuzz the Linux kernel. Sometimes we have to tailor our tool into a very specific domain. How do you the two different directions?
Here are two things I want to mention. One is that paper is a dynamic solution. So somehow they still need some human effort. Our tool is totally automatic, even for some Pixel kernel or some other. So that's one big difference. Another thing is somehow dynamic solution do not have maybe I can show another result. So the coverage of dynamic solution are not better than the static one. So here, in fact, the KSG is another dynamic solution to generate the Syscall description. So somehow they better in some aspect, but the coverage is they cannot cover all the drivers. One reason is just like the last presenter. They mentioned that we can insert some USB device. And then it would appear a new device file in the Linux kernel. And the dynamic solution somehow would miss them.
Please.
So I have a question about the findings of your results. So when you do analysis for Linux kernel, we know there are a bunch of Linux drivers, and also the KVM appears to be it starts with init as well. The format is similar to with a Linux driver, but it has 2 kills to be installed in the Linux kernel. So when you do the findings of your description, did you find what are the key difference between the KVM driver and the other drivers?
First thing is at least in the source code level, the KVM is a kind of so-called MISC device driver. So in the source code level, there are no difference. Fundamentally, they are the same. But in the logic level, they are totally different. But one thing is KVM is one of the complex driver. As I mentioned, some L control of KVM could return some file descriptor, and there are more dependency on some other things. So I can say maybe KVM just complex and know some fundamental difference. But also the argument type of KVM also complex, but fundamentally they are the same.
So one follow-up question, sorry. So could they identify the hypercalls interface as well, or just the interface to user space?
Here you mean some indirect call inside the KVM?
Hypercall is like a call to the QEMU will call through the Syscall and then through the hypercall to create the VM.
That's out of the scope, I think, because we focus on the code inside the kernel. So you mentioned is the KVM called some QEMU code and in the host of the kernel, right?
Yeah, the virtualization Syscalls, yeah.
Yes, this is out of our scope. So somehow, maybe you can still test them by the Syscall of the host machine, I think.
Okay, got it. Thank you.
Great. All right, let's thank our speaker one more time.